Ranjan and my registration number is 17BW0134 and I present to you my physics digital assignment, that is recording a video and explaining a concept that is in our syllabus. I have chosen to explain the concept in quantum mechanics, a particle in a one-dimensional box. So let us begin. Please don't mind the handwriting. Yeah, okay, so particle in a one-dimensional box. Consider that a particle is constrained to move only about the x-axis from the limits x is equal to 0 to x is equal to L and can move infinitely in the y direction and the z direction. So basically it's in like a well that's confined only about the x-axis. Let me explain it to you. X is equal to 0, x is equal to L. About the x-axis. That means the particle can be anywhere in this region, right? And these two boundaries can extend up to infinity. We obviously have to confine the particle in a box, so we can at least approximate whether it is in the box or not in the box. As Schrodinger had once performed with his cat. So yeah, from x is equal to 0 to x is equal to L, we know that the position might exist. So we know that if the particle is in the box, the potential is 0, right? So the potential inside the box is 0, and if the particle is not there in the box, just like our earlier assumption, the potential right outside the box will be infinity. So right outside this range b is equal to infinity, and right outside this range b is equal to infinity. So that means the particle inside, when the particle is inside the box, the potential is 0, and when it's not, it's infinity. Now, obviously, we need to have a mathematical backup for all of this. So, the equation is as follows. This H gap is called the Hamiltonian operator. And it is given by the formula. Wait.
Start.
Okay. H cap by 8 pi square m into d square psi by dx2 plus b. Plus b. So now, on substituting this value in the initial equation, we get minus x square by 8 pi square m psi into d square psi by dx2 plus b psi is equal to e psi. Yeah, is equal to e psi. So this is what we get from substituting the Hamilton operator in this equation. And this equation on rearranging, we get minus h square by 8 m d square psi by dx2 into pi square m d square psi by dx2 plus b psi minus b psi is equal to 0. And this can be, this on further multiplication with 8 pi square m by h square. So we can make a constant multiplied by 8 pi square m by h square. So on multiplying the constant, we get d square psi by dx2 plus, we can rearrange this because this is a negative sign. If we take it to the other side, we get plus 3 minus b psi times 8 pi square m by h square. Is equal to 0. And now this is an important equation to us, so I'm going to box it here. So now let's take it back to where we started, and we assume that inside the box the potential is 0, and right outside the box the potential is infinite. So let us substitute this equation in terms of what we had discussed initially. I'm going to come back to this side. Yeah, okay. So on substituting here, outside the box. So here for B we substitute infinite as we discussed initially, which implies d square psi by dx2 plus e minus infinite psi times 8 pi square m by x square is equal to 0. And this is possible obviously only when psi is 0, which implies psi is equal to 0. And we know that the probability density is given by psi square, and 0 squared is 0, and hence there is no possibility that the particle can exist with these constraints. Hence the particle is not outside the box. Pause. Now that we've discussed what happens outside the box, it's time to go inside the box where the real action is happening. So inside the box, I think I'm going to come back to it. I'm just going to write this equation here because it's a fundamental equation. And d square psi by dx2 plus e minus b psi into 8 pi square m by x square. Yeah, so now back where we started, let us assume we are looking inside the box. So inside the box, we know that b is equal to 0. Inside the box. Yeah, so if b is equal to 0, on substituting b is equal to 0 in this question, we get d square psi by dx2 plus e minus 0 into psi times 8 pi square m by h square is equal to 0. And now this can mean something, right? So instead of say 8 pi square m by h square, we're going to call it a constant. We're going to call it a square because it's very big and annoying. So this, even this e is invisible to a square because we can, if we remove the e as well, we can make it a second order differential equation in terms of psi alone, which gives us the probability density in the time. So 8 pi square me by h square is k square. Now on further writing the equation, we get d square psi by dx2 plus k square psi is equal to 0. And this equation obviously looks better, right? Wait, this is actually h half square, and that is given by h by 2 pi. Yeah, pause. This is given by h by 2 pi. So yeah, after that, because now that the particle has to be inside the box, that means this equation somehow carries the particle, right? So now let us assume that we know that the wave equation can be given as, that is the psi, can be given as wave equation, which is, this is just a normal wave equation. So this is a sin kx plus b cos kx. Alright. Now, where a and b are constants, they are some random constants. Yeah, okay, I hope you understand that. So now, this is a wave equation, and let us try this at both the constraints within the x-axis. That is from x is equal to 0 to x is equal to L. So when we substitute x is equal to 0, when x is equal to 0. This equation we get psi is equal to a sin 0, a into 0, which is 0, plus b cos k into 0, which is which is also 0. No, this is 1. Yeah, we know that the psi at this point has to be 0 because the particle is not psi. We know this psi of 0 is equal to 0. And now, this is psi of 0. Yeah, now on substituting b cos k of 0, we get that b is equal to 0, which is a very important result. So our equation further becomes psi is equal to a sin kx. And now on substituting, when x is equal to L, we get psi of L is equal to A sin KL. As the B term has gone completely, we get psi is equal to A sin KL, and we obviously need to know that psi of L is also equal to 0 and psi of 0 is equal to 0. This exists between and not at the constraint itself. So psi of L is equal to 0 too. So now on substituting this, if we equate this to 0, A is a constant, so A can't be 0. So sin KL is 0. Right, sir. Sin KL is equal to 0. And we know that sin KL is equal to 0 when this is the form of n pi, which implies KL is equal to n pi, and hence we get the value of k is equal to n pi by L. False. Yeah, so now we get the value of k is n pi by L. But we also recently got that the value of k square is given by 8 pi square m by h square. So let's go back to that. Now, on equating this, we get n square pi square by L square is equal to 2me by h square into 4 pi square. Right? As we had discussed in the previous equations. And I think I made a mistake here. This is h square and it's not h square. Try to get back to that. Yeah, but this is also an important fact to be. So yeah, because I realized that I made a mistake because this equation might have gone wrong. So on further solving this, you can cancel the pi square and pi square. Okay, basically on solving it, we get the value of E to come out as n square h square by 8 m L square. Right, on solving this equation, and this is different. This is called an eigenvalue, and this is obviously less. On substituting different values of n from n is equal to 1 to n is equal to n, we get E1 is equal to x square by 8ml square, E2 to be 4h square by 8ml square, E3 to be 9h square by 8ml square, and it goes on as a square relation. Pause. So, yeah, okay. As these eigenvalues, as from these eigenvalues, it is clearly proven that energy is quantized, which was one of the first postulates suggested by Feynman. So, energy is quantized. At the end of the day, we always need to remember this. Yeah, okay. So now so now that all of this is verified, there's just one last bit to all of this.